Alrighty, hello. Welcome back to video number 2. I'll be picking up pretty much right where we left off after the first introduction to kinetics. So we talked about what does rate order mean. Well, we're talking about the atoms. We looked over our formulas. So now let's go into some more of the advanced type of question that you can expect on an exam or a quiz. So one thing that's really tricky for some students is when you're given a chart. You might be given a reaction such as 3A plus 4B goes to 5C plus 3D. And I just made this up. Whatever. It's just an example. I don't quite care too much for the specifics because we are here for this here chart. Now, how these problems will typically work is you'll have, trial 1, trial 2, trial 3. And this will be 0.1 molar. This will be 0.1 molar. And we'll have a rate of 10. And then suddenly we decided, okay, trial 2, I'm going to have some more A. And then we see this one up to 40. And then for trial 3, maybe I'm going to change B instead. And maybe it went up to only 20. So you'll be given this problem, probably a reaction, a chart, maybe just the chart, and you'll be asked very simply, write the rate law. I want the complete rate law. So keep in mind, this is a regular rate law. I did not say the word integrated. So write the rate law, please. Well, it's not really a question, more of a command. So what does a rate law look like? Don't forget your skeleton. The rate law looks like rate is equal to K, whatever K may be. Concentration of my first reactant. In this case, we have reactant A and B. So reactant A to whatever order it is, right? I don't know what order, so I'm just going to say X. And then we have reactant B. And I don't know his reaction order either, do I? So I'm just going to pick another variable. Call it Y, because why not? So this is the skeleton of what my rate law will look like. And after I solve this question, I'll be able to tell you what order is A, what order is B, and if I care enough, we can calculate K as well. So let's look through how I can utilize this chart to extrapolate and pull all this information out. So this is what our final answer will look like. And actually, this same equation is what we're going to be using to get there. So one thing that's really interesting is I could set up this equation utilizing one of my lines, right? Like, let's say I just decided line 1. I could say that the rate law for this step is the same skeleton, right? Rate equals K, concentration of A, concentration of B. Well, I can plug in numbers. My rate is 10. So 10 equals K. I don't know what K is, so I'll just leave it as K. I do know my concentration of A now. For here, it was 0.1. So I have 0.1 to some unknown power, right? Multiplied by the other reactant B, who is also 0.1, to some unknown power, right? Power Y. Give me a quick second. I think my music might be too loud. I'm turning that down. I hope that wasn't too loud for the beginning, or else it's going to be really awkward. But anywho. So this is the rate law essentially for trial 1, correct? But I don't know K, so I can't really solve for anything. I kind of got like 3 variables going on here, so that's problematic. And I can do the same thing for every single step. So I'm going to go ahead and do the same thing for step 2. And you'll notice that these look very, very similar. The only thing that really changed was my rate and my concentration of A, right? So everything else is the exact same. So one thing that's really interesting is I always like to try to look at this from the side of small to big, right? So I'm going to think of trial 1 as my beginning, trial 2 is my ending, right? Because I started out at 10, I finished at 40. So what we can do is we can think about, well, how much did my rate increase? How much did my rate increase by? And an easy way to do that, because your question might not give you nice and clean numbers like me, very simply just divide it. So 40 divided by 10. I can think, okay, so my rate went up by a factor of 4 times, right? 40 divided by 10 is 40. And we're going to compare that between our two trials. I feel like I didn't do a good job explaining what we're doing here. So to back up, pretty much what I'm doing in essence is I'm taking line 2, my final, and just dividing it by my initial. And I'll set this up and I'll explain what's going on. I think I can do a better job. So on the top, I have line 2, right? So 40 equals k times 0.2 to the x power times 0.1 to the y power. And on bottom, I'm going to have line 1, which looks like this. How does this work? Let me take another stab at explaining this process. Why are we doing this? We are doing this because this allows me to compare on the left side of my equal sign. I see that my rate increased by a factor of 4. My rate went up 4 times. On the right, once you do all the math, we can see here that k cancels and that this 0.1y also cancels. And I get 0.2 to the x power over 0.1 to the x power. Let me keep extrapolating a little bit. Let me keep doing some math. For my mathematically inclined students, this probably is no worry for you. For those of you who math is scary, anytime you have a fraction and your top and bottom are to the same power, I can write that the same as just the normal fraction as if there was no exponent, and then put the exponent outside. It's kind of like factoring out the exponent, so to speak, and then you can think of it as I could factor it back into both of them if I needed to. So we're here now, and this helps me because I can just do that fraction. 0.2 divided by 0.1 would be 2. And now I can finish the explanation. So once again, on the left, this is my rate. My rate went up by 4 times. It increased by a rate of 4x. And here, I can see that my concentration of A increased by a factor of 2x. And this is only A, because remember up here, when we did the division, I canceled K, I canceled B. So the only thing left on the right side is the concentration of A. Both 0.2 and 0.1 were originally my concentrations of A. So what that allows me to do now is just look and compare. So if A doubled and rate quadrupled, what does that mean about my order? So 2 to what power equals 4? Well, that will be very simply 2. 2 squared is 4, right? And now that I think about it, I didn't really go over this idea. So let me sidestep a little bit and explain something, just in case. I feel like this might be implied by the rate laws, but just to spell it out, to be direct. Whenever I have a zero order reaction, let's say that I have my concentration of A right here, and I don't really care what the original was. Let's just say I'm doubling A, right? How will that affect my rate if it's zero order? Well, think of your rate laws. Your rate law is equal to rate equals K times concentration of A, in this case to the 0 power, right? So even if I double this, rate equals, I'm going to ignore K, it's a constant, it doesn't matter. Even if I were to double this and put a 2 here, 2 to the 0 power is still 1. So this is no change. If instead it were to the first power, and I'm just going to make sure I'm always doubling A so we can see the pattern. Instead, if I were to have a first order, that changes my exponent. So instead, now it's a 1. I have 2 to the 1. So instead now, I have a change in my rate of 2 times. My rate will also double. Notice that this matches. If it's first order, whatever happens to that guy, happens to him. Concentration goes down, rate goes down. Concentration goes up, rate goes up. If rate was doubled, that means my concentration had to be doubled. If my concentration tripled, my rate would triple. First order is very, very simple. Once we get into higher powers, this is where it starts getting a little interesting. If I were to double them, same idea. I'm going to come over here. I change my equation. Instead of to the first power, now I am to the second. and 2 to the second power is 4. This would quadruple. I think the pattern's been established, but to be safe, let's do just one more. Let's skip 3. Why don't we just go big? Let's go like 6. 6th power. That's a G. 6th power. And I W. Well, let's same song and dance. I'm going to go back to my original equation. Going to change my power. I am no longer 2nd order. I am 6th order. And so my rate will be whatever 2 to the 6th is. 4, 4, 4. Is that 64? Someone double check me on that. Whatever 2 to the 6th power is, right? Don't trust the 64. That's a mental math. But anywho, I hope this helped to illustrate the relationship between your rate order and how changing you will affect rate. I hope that helped explain that. So, moving back to our question, we have established, just to recap, that A is 2nd order, right? And if we look back, I can this was the long mathematical method, right? Now I can show you the shortcut. With A, I can see that A went through a doubling. Well, what happened to my rate? My rate went through a quadrupling. And obviously my B was unchanged, so that means I get to ignore you. So, well, if A doubled and rate quadrupled, that means I can set up this. I can think of it as, okay, 2 to what power equals 4? 4 because of a quadruple, right? And then I can just go straight to my answer of x equals 2. Notice if you do this little shortcut of just looking at it and just kind of extrapolating it this way and converting that into an equation, you skip a lot of fun stuff. So heavily recommend this method, although it can be quite difficult whenever you have, you know, a rate that's 0.1356 and you have all these decimals. So I get not being able to do it all the time. If you're able, though, heavily recommend this method. Anywho, so now that I've shown it twice, I'm going to go ahead and just go to my skeleton over here, and I'm going to slap in my 2. So, okay, I now know that A is 2nd order. Now I just need B, and then all is Gucci in the world. Well, how the heck do I get B? Good question. So, much like with A, we picked lines 1 and 2 because B was constant, and when something's constant, I get to ignore him. Well, I need to look for 2 trials then where A is the same, so I can ignore A. Luckily for me, lines 1 and 3 have a exact same concentration of A, meaning if I zoom in on lines 1 and 3, I get to ignore A. And I'm going to display the shortcut in full effect. All right, B. What did B do from trial 1 to trial 3? B doubled. All right, what did my rate do? From trial 1 to trial 3, my rate also doubled. Okay, so because B doubled, that means 2 to the y equals 2 because my rate doubled. Well, 2 to what power equals 2? I think y equals 1. And that means I have completed my rate orders. I now know the rate orders for both of my reactants. Well, sometimes they want K, and if they ask you for the entire rate law, you can probably assume they want K. How do I do it? It's not too bad at all. It's a little tedious, but it's not bad because if you think about it, I get to just go look at this chart, pick a line, and plug it in. Because if I want K, that means I need a rate and I need my concentrations. If only I had a place to go get those 3 things. Oh yeah. So we can go ahead and just go straight to solving and plug and chug. So my rate is 10 for line 1. K is what I'm solving for. I have 0.1 squared. I have 0.1 to the first power. I hope I don't scare any people who aren't math fans. That'll be 10 to the negative 3. All right, so K equals 10 divided by 10 to the negative 3, 10 to the 4th power. That equals 10,000. I will verify that on my second monitor, doing some calculation, and yep, 10,000. Cool. So there we go. Now I know my K is 10,000, and if I wanted to be super cool and write an entire complete answer, I would say that the rate law for this question is that the rate equals 10,000 times, I'm going to leave some space, times my concentration of A squared times the concentration of B. And you don't have to put the 1. You can if you want to, but I typically don't because it just looks cleaner. And I'll let the space here because just in case your professor is a mega stickler, let's review an important idea of your units. So I know I am second order for A and first order for B. From the previous video, you might remember that your units of K depend on what order you are. Well, do I do the order of A, the order of B, both or neither? To those of you who said both, very good. I care about my overall order. What is the overall order of this reaction? In this case, it'd be 2 plus 1. Just combine them. I have a third order reaction. Yes, that exists. No, don't worry about doing math with it. You go as high as 2 for your typical math. We can handle this. So, also from the previous video, you might remember how I typically get my K units. I think of the 0K. The 0K is very simply molarity per second. And then, for each order that I have, I'm going to add an M on bottom. So in this case, I'm third order. So I'm going to slap 1, 2, 3 M's on bottom. 1 M cancels on top with the bottom. And I get a final units of K of 1 over molarity squared times seconds. So if I wanted to write my units in here just to be a super cool, superstar, straight A, full answer student, bada bing, bada boom, this would be your complete rate law for the chart. Not too bad. Hope that explanation made sense. If not, comment section. Or again, if you're my student, text me. All right, so moving away from charts now. Let's go into something I alluded to in the first video, which was a mechanism. What do I mean by a mechanism? So you, throughout your chemistry career, probably by this point, have learned a lot of reactions. And I'm just going to make one up. Something like, 2A plus 3B goes to 4C plus 2D. I think I copied the previous one correctly. And this would be my overall reaction, right? Like I mentioned in the first video, or like I posited, can I determine my rate law, my rate order, from this overall reaction? Do I have that ability? Give you a minute to think about that. Think of what you would do. And time's up. Nothing you could do. If I only gave you this, you are completely out of luck on how to determine rate order, right? I didn't give you a chart. I didn't give you no numbers. I didn't give you crap. What we talk about in this section of the unit is mechanisms. And that's that this reaction doesn't happen all in one go. It's not like I'm going to just see all at once 2A molecules and 3B molecules smash into each other, explode in a nice bucket of confetti, and then I get 4C and 2D. That's not realistic. What ends up happening is that it is in pieces. So maybe the first step is that an A has to react with another A. Maybe step 1 is to create A2. And that's because A2 is very important to then react with one of those B's to create A2B. And then maybe, just maybe, we also need those 2 remaining B's to react and make B2. And for some reason that has a off product of 1C. And then in the final step, that A2B and that B2 are going to smack into each other, and then that's going to explode into a confetti of 3C plus 2D. This is a whole lot. Mr. Griever, what are we doing? There's so much on my screen. Relax. A very good thing I like to do is, just because sometimes I don't give you this, you don't get the overall, let's just step one, turn this from a list into my overall reaction. So what am I going to do? I'm just going to add up everything I see on the left and everything I see on the right. So I see 1, 2 A's on the left, so I have 2A. I see 1, 2, 3 B's. I see an A2, a singular A2. I see an A2B. And I see a B2. And I'm doing the same thing on the right. I see an A2. I see an A2B. I see a B2. I see 1C plus 3. I see 4 C's. And I see 2 D's. And this is a whole lot because I have some stuff on both sides that I can cross out. And wham bam, thank you ma'am, you can tell, you can see that we match our original equation. Not required, just good to do. I think having your overall reaction can be very beneficial. Now there's one more piece of information that these problems will typically give you. They will say, hello, I am the slow step. These guys are fast. So, your question for this problem, what would it ask you? Very simply, what is the rate law? Just like the previous chart questions, I just want to know simply what is the rate law. With this one, there's no way to get K because we don't have any numbers, right? I didn't tell you how much A, how much B. We don't know what the speed is, what's the rate of any of these steps. Only thing you know is this guy's slow. So, the secret sauce for this type of question is that we need to identify and utilize our rate determining step. That's the keywords that I mentioned last video. And well, what is a rate determining step and who is it? Those of you with more pattern focused brains might be able to just wager a guess. And yeah, I'll just go ahead and say it. It is the slow step. Why is it the slow step? Well, let's imagine for a second that this was like a 4-legged race in, I don't know, track and field. And step 1 is not our fastest racer. Homie takes an entire hour to complete the race. Steps 2, 3, and 4 are all on one and can finish in 2 seconds. Maybe this one's 4 seconds. And this one is 0.1 milliseconds. This is not an unrealistic comparison between the magnitude of speeds. Some reactions are just way, way fast and some are way, way slow. So if I were to tally up my time, of our 4-legged race, it takes 1 hour, 6 seconds, and 0.1 milliseconds. Do you think the 6.01 seconds, or whatever millisecond would be, 6.001 seconds, matter compared to the hour? Not really. It's negligible. If I were to completely ignore all of my fast runners, my time doesn't change much. 6 seconds is, I don't even know what percentage of an hour. Not a lot, right? So pretty much for the sake of a rate law, we can just ignore our fast steps because they're so fast that the only thing that really determines my rate law is going to be my slow step. So we get to completely ignore my fast stuff. And I'm going to zoom in just on this step right here, Mr. Step 1. And writing the rate law is actually super easy. You're just going to look at your reactants. Well, don't forget your K. Rate equals K times concentration. What are my reactants? I have A. All right. How many A are in this step? 2. Alternatively, I could have been nicer and written this how you will probably see it on your exam, so I will switch to that style to match. Notice, literally, I just stole his coefficient. You can do that now. If I give you the mechanism, only if I give you the mechanism, then your coefficients are equal to your rate law. Why is that? Because remember back when I explained rate order in the first video. Do I still have that drawing or did I erase it? I erased it. In the first video, I gave the example of 2a plus 1b making a2b, right? That's because what I was saying is at this step, I have 2a molecules flying in to 1b molecule. I have a 3-point collision, and we create a2b. Remember, your order is how many atoms are colliding. Right here, I can see I have 2 molecules of A colliding. Therefore, I am second order. It only works here because this is my rate determining step. And you might want to get used to that word, rate determining step, as you might be hearing it quite a bit over the next week or so. So, because it's the slow step, the rate determining step, I can go straight to my rate law. You're not able to find K. You will not be asked for K. Panic not. This is a complete and true fine answer, right? So, when it's simple, this is really easy. This is very straightforward. Look for your slow step. Look at your reactants. Bada bing, bada boom. Goodbye, right? Things get a little interesting once we start changing stuff up a little bit. I'll keep this the same, except I am going to change who the slow step is by a little bit, and we're going to see how this can cause some issues. I'm also going to change one thing because it's a little important. We'll talk about why. This step's going to be equilibrium. It's going to be fast. It's going to be equilibrium. They might spell it out for you as equilibrium. They might not, but just watch your arrows. And now this step will be my slow step. So, okay, not a whole lot has changed. So let's approach this the exact same way, shall we? So what step do I care about? I care about my rate determining step. Who is my rate determining step? Well, that would be my slow step. So I am looking at Mr. Line 2. I'm going to look at my reactants and just easily write them in. So I have A2 to the first power, right? Because there's no coefficient, so it's a 1. So it's first order for A2. That's first order for B. Okay. And that's my answer. And if you were to box this in and submit this, you would get no points. Because we missed something. And I think the best way to explain the problem is let's think about how my reaction would look at the beginning. Like when I'm about to do my reaction. I'm in the chem lab. I got my beaker. Maybe I already got my A in the beaker. Maybe I already got my A ready to go. My first reactant's ready to go. And then I just poured in the B, right? This is the B coming in. So I want to talk about the exact instance that there is both A and B in this beaker. Once we have A and B together, assuming no reaction has happened yet, right? I could think of this as I have 100% of my original starting A, right? If I started with 10 moles, I got 10 moles right now. If I also added 10 moles of B, I would still have all 10 of those moles. I have 100% of my reactants. None of them have left yet, right? Well, how much of my products do I have? It's a little bit of a weird question, but I have none. There is no C. There is no D yet. Once I let the reaction happen a little bit, you know, if I flash forward maybe half a second, I might see a little bit of my other, well, of my products, right? I might make my C and D, right? But at the very beginning, there is no C and D, and there is no A2, for example, who is in my rate law. There is none of him. So at the beginning of my reaction, if I were to use this as my rate law, rate equals K, let's say my K was hypothetically 10, it'd be 10 times concentration of A2, there's none at the beginning, so 0 times B, which let's say I had 10, my rate would equal 0 because I have no A2. If my rate is 0, my reaction is not happening, so my reaction won't proceed, so I won't make any product, and I won't make any A2, and I'm stuck. So this rate law isn't correct, because it wouldn't make sense for my reaction not to happen. So what gives? Well, what gives is this A2 is the problem because he is something called an intermediate, which I'm sure you've talked about a little bit before. But just to review and go a little more in depth, A2 is an intermediate because if we look at our mechanism, you can see that in step 1, A2 is created. A2 was not originally present. It was created to be used immediately. A2 is not present in my overall reaction. It was created, then used. That is the definition of an intermediate. So a species that was created in your mechanism and used also in your mechanism. So I need to get rid of this. I need to find a way to substitute A2. And substitute. Okay, I spelled it right. One thing I'm going to do for the sake of labeling, I'm going to label our Ks. Let's call this K2 because this is just from this first one. Keep in mind, this is a capital K because it's equilibrium. I'm not good at showing a capital versus a lowercase. So I'm just going to write the one super big. But notice we have different Ks for each step, right? It's going to be important because I need to think of a way to replace this guy. How can I replace A2? Well, why don't I just start by trying to write the rate law from A2's line? Maybe that could help me out. Maybe I could use that and get rid of it somehow. So the rate law for the line that created A2 would be line 1. And it would be that rate is equal to K1 times that reactant A2, that other reactant, oh wait, whoops, I'm looking at the wrong line, excuse me. Line 1 would be A squared, right? Well, okay, I wrote the rate law for line 1, and, oh no. It does not have A2. And this is where an important idea from your equilibrium unit sneaks in. What is the definition of equilibrium? I'll give you a second to think about that. What is the definition of it? I think it's a long enough second. Equilibrium refers to a state in which your forward rate equals your reverse rate. So if this is making 10 molarity per second, this is also making 10 molarity per second. That's because you're achieving a state of a constant concentration of your reactants and products, right? That means any forward traffic must equal reverse traffic. That is also the same for your rate, as shown here. So what that means is I can flip reaction 1 around. How would I write the rate law for the reverse step? Well, the reverse step would mean that this guy would be my reactant, which means the reverse would be the concentration of A2. And it also needs a K, so we just call it K -1. Negative to tell you it's the reverse reaction, right? And I know this is equal to the forward rate because it is equilibrium. It's a little complicated, so I'm going to back up a little bit and I'm going to explain that again start to finish just to make sure it's cemented. The problem with our original rate law in purple is that I have A2 in my rate law, and A2 is an intermediate who has no concentration at the beginning, so this rate law would be 0 at the start and kind of be deadlocked and not move. This equation just sadly does not reflect the true rate law due to having the intermediate. I need to get rid of the intermediate. I need to think of other equations that will utilize A2. The only way I can get equations with A2 is to look at the step that made A2. So I am looking at line 1. I start by writing the forward rate law. I see that that forward rate law would be that rate is equal to K1 times A squared. Well, that doesn't quite have my A2, right? So I need to remember that this is equilibrium and that the forward and reverse rates are equal. So I can equate that forward rate law that I just wrote with the reverse rate law, which would have my A2. What this allows me to do now is I can just do some algebra and solve for A2 by dividing both sides by K-1. And I get that the concentration of A2 is equal to K1 times A squared over K-1. And now I can substitute. I can take my original answer, rate, and I'm talking about this one again. Rate equals K2. And now that I get to A2, I'm going to substitute in K1 over K-1 times the concentration of A squared. I have substituted A2 away, and now I plug in B. This would be my final rate law. Some professors, answer choices, and students prefer to just call this one big ol' K. Why? Because this is ugly. You just call it KC, and that would encompass all of your combined Ks. Although, author's note, if your professor is a stickler, make sure you write somewhere on your paper KC equals K2 times K1 over K-1. That way your professor knows what the crap does that mean. But that is the intermediate removal, so to speak. The question of how do I deal with writing a rate law when I have an intermediate. And it is a pretty involved process that can get pretty ugly, but this is the basic breakdown. I'm hard pressed to think of, oh, never mind. I have one more idea, and it's a really short and sweet one. I kind of talked about it in the first video, but one question that I usually had on all of my kinetic exams in pre-AP and AP and Gen Chem on the kinetics unit is some variation of this. The scenario is, okay, I am an undergraduate chemistry student, and I have a reaction that I am testing. The reaction I am testing is A goes to B. And my professor asked me to determine the rate law for it. Okay, that's not a big deal. So me being the clever guy I am, I go to the chem lab and I run the reaction with a whole bunch of little probes in there and different instruments that allowed me to record the concentration of A versus time. So pretty much I have two lists of, like, you know, my initial concentration was 100, time is 50, or time at 0, and then 90 at 10, maybe I'm 85 at 20, blah, 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 etc., right? But I'm not going to show you these numbers. Instead, what I'm going to tell you is I went to Microsoft Excel and I plotted my data on 3 different graphs. All of them have time as your x-axis, but my y-axis is different for each of these. I graphed 1 over concentration, I graphed just concentration, and I graphed the natural log of concentration. My first graph looks like this. My second graph looks like this. And my last graph looks like this. Your question is very simply, what is the rate order of this reaction? 0, 1, 2, because you don't work with 3, 4, 5, 6 plus. This is a very simple question, actually. If you remember from the first video, I mentioned the reason we integrate. Why do we integrate? The reason we make these integrated rate laws is to make them kind of look like y equals mx plus b, aka to linearize. So whenever you graph data, two of your graphs will not be linear. That is screaming at you, you messed up. This is not the right order. This graph is linear. So I know this is the right graph. I am zooming in on graph number 3. This is who I care about. Well, okay, Mr. Graph 3, what order are you? Well, I'm going to zoom in on my y-axis. Remember, clear, CLR, 4, 0, 1, 2. We are natural log, we are L. So this is a first order. This question is really simple because now that I've explained it, if I were to try to trick you again with the same question, I'm sure you can answer this in probably 5 seconds flat. Let's try it, shall we? So I'm going to go ahead and write this up. I'm probably going to take more time drawing it than you will take to solve it. What order is it? Pause just for politeness. I'm going to start explaining now. Well, first step, not linear, linear, not linear. Cool, I got my right graph. This is my linear one. I know it doesn't look linear because I kind of curved it, but trust me, it's linear. And I see my y-axis is the reciprocal. And I know CLR. Oh, I'm the last one. That's second order. This is, in fact, a second order reaction. Woohoo. All right. I think that is the majority of question types that you will have in kinetics. Of course, I will review more of the unit, and I will make a third video if needed covering any more advanced questions. Maybe just go over some practice problems. But I do believe these 2 videos should encompass the majority of your lecture material, the majority of your theory, your formulas, and the question types you will encounter in this unit. I hope these 2 videos were helpful. If they were, I'm not going to say the thing, but you're on YouTube, you know what to do. And if you're a student of mine, thank you for watching the full video. We'll talk more soon. So thank you for your time. I hope this video was helpful. Please enjoy the rest of your day.